Perfect. I hope you can see my screen and hear me well. So now continuing from the previous talk, and this talk is going to be more about learning supervisors when you don't have plant models, but just specifications given. And yeah, as it was a continuation, it was done in collaboration with Frederick and Martin as well. Some background. I want to start with this background from a paper almost 20 years back, 18, 20 years back, and where modular supervisors or modular synthesis was defined. So here they take given a plant of several automatons and a specification again of several automatons, then generating a supervisor is basically creating one supervisor for each specification. And to do this, you basically synthesize the specification with a subset of the plant modules. And there are basically two main elements spoken about in the paper. That is, one, you directly synthesize what I call full synthesis. You directly synthesize a subset automata with the specification to get a maximally permissive supervisor, or you do it in a more incremental manner. Only taking those subcomponents that are needed and then iterating it till you have a maximally permissive controllable supervisor. And this will kind of be the base for the contribution we have. So let's define the problem. So we have a specification automata with a set of specifications. We have a PSH, and if you remember from the previous talk, a PSH was basically a three-tuple with defining the modules, names of the modules, a set of events for each of these modules, and a set of variables in the actual simulation that correspond to each of these modules. And then we have the simulation that we can communicate with. So the question then is, can we learn a supervisor? And once we've learned it, we wanted to check what kind of properties this supervisor will have. So again, we're trying to follow the same method as followed previously, but just that we don't have the plant models, right? So we want to be able to replicate that in some way. So we again start with the same assumption, one supervisor per specification. And then we want to now update our PSH. So our PSH is going to be the core of our learning. And we will learn one module for these, one supervisor, but, we learn one supervisor for each specification, but this specification has to be in conjunction with a subset of modules defined in the PSH. So how do we define these modules? How do we choose which modules need to be learned along with a particular specification? So that is done basically in the same way. You have those modules that directly share an uncontrollable event with the specification, and those modules that indirectly share. By indirectly, I mean, first you check those that are directly sharing, and then those modules in turn will have uncontrollable events shared with other modules, and then you keep overlapping them. For this, we use the definition of event dependence. What this basically says is, given a set of modules M and an alphabet sigma prime, you will choose only those modules that share events with sigma prime. So using this definition, we can start creating the set of modules we need, right? So, and it's basically taking the uncontrollable events from the specification and putting all those modules into one, so to say, bag, or creating one set there. So this first part here basically does the direct relation for the modules. The second part here is basically repeating the same procedure till you reach a fixed point, looking at indirectly sharing modules. So you can run this and you will have a set of modules, which is again a set, but you can just consider it to be one single set of modules, right? We can look at the details with the example later on to make it further clear. But you can take this, you can take these modules and the algorithm I define later on, you can use them together and you will learn a supervisor that is maximally permissive and controllable. However, this directly or very quickly leads to a monolithic learning, which is inefficient and which we want to avoid. The reason being, when you start collecting all indirectly shared events, modules with indirectly shared events, you end up with something, yeah, it snowballs, right? It snowballs and it possibly can include all modules, making it monolithic. So how do we do the incremental learning and synthesis? So we just follow this procedure here. We learn a supervisor for each specification with the modules that are which directly share uncontrollable events. And then we can, once we have these modules, we can use existing tools. In our case, we use Supremica, and then check if these are controllable. If not, we just synthesize them together to get our required supervisors. But there's one catch there. We might end up learning a smaller subset of plant components, or you end up learning a supervisor that only captures some plant components, not all plant components. And then if you want to synthesize this, you need the additional plant component itself. So we define or we get these components by just doing a set subtraction between the known the union of all the specific modules we have chosen with the modules in the PSH. In the similar way, we update the event mapping and the state mapping to be a union between the specification events and all the events for each of the modules contained in the set of modules we have chosen. And the same with state variables. So now we have kind of updated our PSH. We can call it a new PSH with M prime, E prime, S prime, and K prime. So M prime is basically the union of the specification modules you want to learn and the plant modules you want to learn. And the event mapping and state mapping, again, mean the same thing. You're basically mapping between the module you have to the events that will be in that particular module. We add this K here, and I mean, in this presentation, I'm not going to get into the details of that, and it's basically to keep track of your specification to check for controllability. But it's more of it's more an implementation requirement rather than a theoretical definition. So now we can apply the modular learning, what we saw in the previous presentation. I will not go into the details of it, with slight modifications. These modifications relate to checking controllability. And we come to that when we use the example. I will show you what modifications are needed to learn a supervisor. And then we can learn a set of supervisors. Great. So if we talk about an example, in this work, we looked at the cat and mouse example. And it's a pretty famous toy example we have in the community, right? So you have a set of rooms, in this case, 5 rooms, all numbered 0 to 4. And then you have different doors between these rooms from which a cat or a mouse can pass through. So the events C1 to C7 represent where the cat can move between the rooms, and M1 to, I guess, M5, M6 is where the mouse can move between. All these events are controllable other than C7. C7 is an uncontrollable event for the cat. So given this example, we would like to learn a modular supervisor for this. So we have specifications, and the specifications basically say, I guess this is too small for you to see, but in any case, the specifications basically say that both the cat and the mouse cannot be in the room at the same time. So if you take, for example, room 0, it says, so here, if you're in this particular state, it means that the cat is in the room, triggered by C3 or C6, and it can leave the room with C4 or C1. And on the other end, we have the mouse. So the mouse can enter the room with M3 and M6 and leave the room with M1 and M4. So you have a set of 5 specifications for one for each room. What is interesting here is only 2 specifications have an uncontrollable event, which is C7. And the specifications are specification 1 for the room 1 and specification for the room 3. So if we go back to the diagram, only these 2 share the uncontrollable event. So when we learn a supervisor, we can just learn a supervisor for these 2 specifications, and the rest of the supervisors can, rest of the specifications can be treated as supervisors. All right, so how do we then create our, before going to the generation of extended PSH, we have a simulation, and the simulation has, so we basically wrote our own simulation to do this. The simulation has 4 different rooms represented by R0 to R4. And the variables it uses internally is 1 variable for the cat and 1 variable for the mouse. So this is basically an enumeration, right? R0 to R4. So initially the cat is in room 2 and the mouse is in room 4. Once you have this, and then every time a transition occurs, you can change the value of var C to the respective room. That was our simulation. We defined the PSH as follows. We wanted to have 2 modules, cat and mouse. The event mappings are straightforward. So is the state variable mappings, where the cat has 1 variable and the mouse has 1 variable. So this is kind of straightforward. We created this simulation as an example. So then let our algorithm run. And this is how we would extend the PSH. So you want to learn a specification for the you want to learn a supervisor for specification room 1 and room 3, and both of them have only a cat module in them. So this extended alphabet event set would basically be KR1 union the set of cat events, and same for KR3. Variables for state mapping KR1 is again the same. They contain variable C. This variable here, as I was saying previously, is it basically maps the variable in the specification. So we use variables to keep track of, specification as well. So that's why it's here, but it's just an implementation detail. You can modify it and keep track of it in any way you like. So ultimately, you end up with, you want to learn 2 specifications and 1 plant mouse. The reason for this is that if you notice, we do not, let's say we learn these supervisors without MG, and then you cannot verify or you cannot check whether your learned supervisors actually behave controllably, because you're missing a plant module itself, right? So we want to learn the plant as well, since it's not going to be included in the supervisors. And yeah, the remaining specifications are treated as supervisors. So what is the learning algorithm in this case? It follows the same structure as before. It's going to be a breadth first search over the entire state space, but we do it modularly with the PSH. So you reduce the state space when you're searching, or you pick and choose which states you want to explore and which you do not want to explore. The difference comes in when you're learning the supervisors, you need to keep track of the transitions in the specifications. And if this transition, so every time you find a transition and you can check in the specification to see if it is uncontrollable, then you need to forbid the state from which you have found this transition. And then basically do not explore the forbidden states. At the end, you can do a pruning algorithm just to remove all your forbidden states and anything that is uncontrollable after it. The details you can find in the paper. I did not want to put in the whole algorithm here and make it more confusing for the lack of time. So you end up with such modules. These are just examples here. So it's a standard supervisor you would learn for such a system. And you can also learn it, or you can also test it out in Supremica if you have it. But yeah, I just keep these here in case someone is interested to see. One thing I can point out is these variables here, the state map. This was the kind of change we did. We know what specifications are within the state variables itself. So that was one thing I did not cover in the presentation, but it's there in the paper if you're interested. So yeah, room 3 is the same, and you learn the plant model, which is here. Just as a side note, I guess so there might be some confusion with the marked states. I am not currently interested in the marked states, and my thinking is that I treat all states in the plant model as marked, and it is a job of the specification to decide what states need to be marked. But in the learning context, it does not play any significant role here, at least. So that's just a side note in case you're confused with the markings on these examples. So now, with the cat and mouse example, the end result is since there is, you can be certain that it is maximally permissive and controllable, and then you can use the existing tools to make it non-blocking as well. In case it was, say, for example, you had another example where you end up learning a model which is not controllable, then you can again use standard synthesis tools to make it maximally permissive. So you have all the models there. The idea is to, so the end result for us is basically to move away from having hand-drawn plant models, but rather learning these models from simulations of systems. Something about decomposable models for the PSH. This is something I also promised in the previous talk. Consider another way of defining the simulation. Instead of variables for cat and mouse, you have variables for rooms, and these rooms can take the value cat or mouse. In this setting, even though the model is valid, the PSH is valid, you cannot learn a modular model. You will learn a monolithic model. And yeah, that is one problem we are trying to solve on how we can define or how we can guarantee conformance between PSH and simulation. And yeah, some concluding remarks. As you could see, we were able to solve synthesis problems when plants were not available, plant models were not available. We have tried this example on the AGV system, and we could solve it, I think, within 40 to 50 seconds with our implementation, but yeah, that might vary. The PSH is really tricky to define, and mainly getting a meaningful PSH is going to take a lot of iterations. Again, the accuracy of the PSH is going to determine the performance of the learning itself. In terms of future work, we want to look at learning more richer formalisms. Right now we are with automata. We want to learn EFAs, for example. And we want to also apply it for a diverse range of examples, which we haven't done so far. It's mainly toy examples we've been running, at least for the supervisory synthesis. Hopefully automate learning the PSH itself by using some, hopefully if that can be done, I guess we will be solving a big hurdle. I guess I'll take questions now. Thank you.
Thank you very much. Very interesting work. Does someone have some question? You can pose now. I think we have time for one or two questions, quick questions. I have one question.
Yes.
But this just an intuitive question. Can you give us some intuition when you can find that PSH is decomposable or not decomposable? Do you have some result, or trying to prove some result that you said, oh, by these results, it's not decomposable?
Yes,
it's interesting.
Yeah, we are currently working on that, but a rough intuition, I would say, is when you start seeing, so as long as you have one event that is going to change one state variable, then we can be sort of sure that this is going to be decomposable. But if your event is going to change multiple variables, or if multiple variables are changed with one event or the other way around, then you cannot be certain that it is going to be decomposable. It varies, but you cannot be certain. But yeah, hopefully we have a paper. Yeah.
But you admit that you have components that share events or not?
We can have components that share events. That is not a problem.
Okay.
The problem comes when the implementation is in such a way that you cannot distinguish between, or it ends up becoming a monolithic system, basically.
Okay. Thank you very much.